Okay. So we will go through chapter 12. There are many issues uh, to study. So issues in beams, we are studying the beam theory and beam deflections. And there are several key issues which we need to study. Uh, there are several one. The singularity function and second order moment of inertia and shear stress, bending of beam with the unsymmetric and cross section and shear center. Some of them, for example, these two topics won't be covered, but I think the most important issue we need to study is the second order moment of inertia and also shear stress in symmetric elastic beam. Actually, the singularity function is that we already uh, study in the previous chapter. Here is the singularity function. The reason why we are using the singularity function, well, sounds too much mathematical, but it is about how to express a non-continuous function. So to express the beam theory in a force of a differential equation, the external force, vertical force, are in terms of a distributed load. This is the Carboni equation. But sometimes the load is not quite distributed load. Could be some, distributed load may be a non-continuous like this, and sometimes a concentrated load, and sometimes they concentrate the moment. Uh, but again, the external force, which is the distributed load, has to be in Carboni equation. So we should be able to express all kinds of vertical load in terms of a distributed load. That's why we need a singularity function. Uh, this is the just a simpler way to express by the we uh, define a function. Okay, we define a functions, and this is the actually we already covered, but I just like to remind again. This is a distributed load, and the concentrate load and concentrate moment can be represented in terms of a distributed load. And this is the way, especially the discontinuous distributed load and this and concentrate and load and moment. This is the way we express. This is the zeroth order and first and -1 and then -2. Well, the for to differentiate from a regular function like the a regular parenthesis, we use the this type of special uh, parenthesis to represent the singularity function. And this is the one we need to follow. This is just the definitions of how to handle these types of function in terms of a distributed load. So as long as we follow these rules, then we don't have to worry much about the other mathematical representations, such as, the for example, this one, x if x is less than a, then q equals 0. If x x is greater than a, then qx will be q0. That can be simplified and like this. So that's the whole point. We define this singularity function to simplify the expressions. And in doing so, we need to follow these rules, integrations, rules. Actually, the integration, since we have this force of the differential equation, we need to integrate. We need to keep integrating 4 times. Then that's the one we need to do so. So we went through the procedures, and uh, finally, when we got the results in terms of Vx and then Mx, because once we solved all of the results, we will have a final deflection, and then we can represent shear force and moment. Uh, so Vx, for example, as a result of integration, so we will have a zero here, and then a moment equal, here is the one here. So by definitions of this singularity function, we can have expressions like that. Uh, so again, the singularity function is a way of simplifying the notation. That is the whole point. Since we okay, the another topic is the second order moment of inertia. That is the very important in understanding beam. Uh, is a definition of a second order moment of inertia. It's partly covered in the statics, but it's very important to go through again now how this second order moment of inertia, or in short, we can just say moment of inertia, can be related to the our beam theory. See, when uh, just 1 second, please. I need to fix my pen. Just 1 second. Okay. Okay. So in the beam theory, the cross-sectional property is represented by I. We have a EI and moment equal curvature. Curvature is the 1 over R, radius of curvature. And this one is further simplified as EI and the V double prime. This is the beam theory. But as you can see that we have an I here. We like to remind ourselves that how and the definition of I is that the y square dA. That is the definition of I. This is the moment of inertia. So we need to separately discuss about this issue. Uh, and here, y square means that the distance. Well, in general, let's define. We can think like the y and z axis in a plane. The This is the cross sections. Any arbitrarily cross sections. The beam can have any cross sections in YZ plane. And then we can define a following mathematical equation of the moment of inertia. Uh, so for example, with respect to this axis, this is the y-axis, okay, y-axis. Then we call y, and the distance. Let's say we have a small area here. That is the dA, and dA and yy by definition is a distance. So with respect to here, we have a certain distance, and then the definition is that y squared dA. So the physical meaning of this moment of inertia is that we like to integrate whole cross-sectional property dA, but when we integrating, we give say kind of a weighting factor z square, meaning that if z is the farther from this axis, there is a more weighting factors, and closer then is the rating factor will be reduced. So the point is that's the scale. And similarly, we can have a moment of inertia with respect to this axis, IZZ, and then IZZ is a distance of this dA from this axis will be y. So similar to this z scale, we have a y scale dA. And another second order, we have a scale. That's why we call it second order. Now we can have define another second order moment of inertia is that with respect to these two axes, this dA could have a y and z, and dA. So this is the totally we can say the IZZ, YY, and IYZ. So this is the definition of a second order moment of inertia. Well, this is just a mathematical expression and definitions, but again, this physical definition, mathematical definition, have a very important physical meaning. Uh, and also, actually, we can define, okay, this is another definition, a moment of inertia tensor, and then we can represent this one as the uh, I dz, I yy, and I yz, and also I zy. So this kind of we call well it can be a tensor, uh, well tensor has its own mathematical characteristics. Well, it is a very big issue, but I just want to make sure that this is the way we represent. So especially YZ, you can define IZY, you can just switch, and then this will be the same. So this is a very similar to a second order tensor representations, something like the sigma, XX and sigma YY and sigma XY and sigma YX. That is the notation wise is a very similar. Okay, so again, this is a definitions. Um, Okay, well, screen seems now all well shared. Sorry, and then it's being well recorded. Uh, Please turn on your camera. Well, there are several students who contact me about uh, the today's class. They will watch the YouTube since class is on Saturday. Otherwise, you guys need to be here. Okay, well, I will continue. So this is the mathematical. I just wanna always make sure that the recording and sharing stops here. Okay. Uh, this is the definition of a moment of inertia. Again, it's just a mathematical expression and definition, but it has a very important physical meaning. Physical meaning, I would say that the cross-sectional property, we can define many different way of the, I would say, Mhm. Just one second. I have some troubles. Okay. Sorry. Okay. Well, mm, Okay. Let's say we have some cross sections like that, any kind of cross section. For the beam, we usually have a rectangular, like the B and H, and or circular cross sections, or like a tube, which we discuss and consider in the beam for the eVTOL. This is the gonna be I'll say this is the OD or ID. This is a typical one. And sometimes we have an I-beam like this. These are very important typical case of the beam cross sections. So covering all these, let's say we have a certain cross sections like that. Uh, Now, the we like to define the uh, property of in general, we can have some coordinate system, and then we can have a define, let's say we define the y and z as a previous case, which like this, y and z. Uh, now, now the point here is that in general, okay, to how to represent what kind of property will this cross section might have. Well, the first one, which we are very familiar with, is the cross section A. A is the cross section, the area. So this is one physical meaning, and also I, which we are studying, Y and this, and then we can this cross section may have many different properties. Uh, I'm trying to generalize the concept of a cross-sectional property. So A, what does it mean A? Well, we know the physically we have no problem to understand this A, but mathematically, what does it mean? It means that okay, we have a cross section. I mean the small area here, say dy and dz. In I mean, A is nothing but the say integrations of dA. So this is the cross-sectional property. So we just integrate over all area. Now, another definition will be, say, property from here, say, y, say this is a z, then z, okay, our z times dA. Say, in other words, there is a dA, this is a dA. dA can be represented by weighting factor of z. So if dA is further from this axis, z will increase. So this is the another way of uh, uh, another property of this cross section might have. I'm gonna sorry, I'm gonna try to delete this one. Okay. And another property can be when we integrating this dA, we can generalize the concept as the g square. Square means that now this weighting factor, this cross section, when we integrate, we can multiply g square. So in general, we can say z n power and dA. So this is the happen to be n equal 0, n equal 1, and 2, and so on. So this is the in general the cross section can have a uh, very different characteristics. Okay, now we are familiar with this one. This is the A, uh, and this is called I. And this one is that we when we integrate A, we just multiply Z, means that this is a we are using this equation to define the center of cross sections, centroid. Uh, I'm trying to tell you that this moment of inertia is one typical definitions of these properties of, I mean, cross-sectional properties. And then you can compare to this one. So Z scale can be generalized. That's the one thing we can keep in mind. Now, these definitions, this scale, and say this is the coordinate system. This is the small z. Okay, this is a small z and then small y. This is a y and a large. Now, these two coordinate system have a distance yd and then zd. Okay, so this is the one coordinate system. I would say we define the properties, one coordinate system. The point here is let's say we are given yy, say z square, dA, and so on with respect to this coordinate system. Now, let's say we have another coordinate system and y and z here, which is with the distance of yd and zd. We like to calculate Iy, with respect to this coordinate, and so on. So let's say we have a moment of inertia, one coordinate system, and how do we calculate moment of inertia in another coordinate system, which has the distance of the yd and zd. So by definition, IZZ, is that from here to there, this is the y, and y is this is sorry, there's a little bit of needs a correction like this and small z. So large y is that we can mathematically, the distance is this small y and then yd. This is a large y, right? This is the coordinate. And by definition of this large y, we can substitute here, and then IZZ can be written like that, right? And then we can simply integrate with scale, uh, and then we have a y scale, and then here y times yd, and and the second one is a yd scale. Now here is that the point is that yd is the constant regardless of this uh, the scale and the uh, this dA. So yd is a constant, and then it can be out of integration. So this is out of integration, and this is also out of integration. Uh, and this one, by definition, IZZ is a this cross-sectional property. We can have a IZZ with respect to this coordinate system. And then here YDA, we D two y's over YD, and what is this? Square DA. This is A, cross-sectional area. Now here, the point is that when we calculate this one with respect to this coordinate system, and this is the result, we can have it. So this is the one, and this is the I mean this can be related. And now here, very importantly, if this coordinate system, if this go through a centroid, this by definition of a centroid, this will disappear equals zero. I mean here, this one, if go through centroid, this YZ coordinate system go through a centroid, this will be a zero. So this is a typical case. YZ, I mean small YZ, go through a centroid, then this term will disappear. Then this will be further simplified to like this. And then this is we consider only YZZ. We can also consider YY. In this case, the Z will be like this, and then a result will be pretty much the same. And YZ is pretty much the same. And this is the one we like to understand. We will make a full use of it. So as long as we know the moment of inertia with respect to a centroid, then we can easily calculate the moment of inertia in other coordinate system. Simply YD is again the distance between the coordinate system, and multiply A. Okay, so this is the one very important result. This is called parallel axis theorem. And you guys, as a mechanical engineer, got the we kind of went through this subject. And now another one is that not only just a translation like this. I mean, the coordinate system is just the translate y-axis and z-axis a certain distance. Now another one is the rotation. Say we have a coordinate system y and z, and now new axis y and z. There is a rotational coordinate as a theta. Then now the point is that how to calculate this y and z. Okay, y and z. Given this coordinate system. Okay, that's the what we like to do. Well, this one, we do use that coordinate relations, this uh, y and z, and this large character y and z. We have relations. Mathematical, the matrix wise, we have a coordinate like this, and cosine theta, and minus theta. And then this is a sine theta, and this is a cosine theta. And then this is the y and z. We do know this one. So this, well, this coordinate system is a little the reversed, but it doesn't matter that much. So the point here is that, sorry, I need to delete a little bit of this. This is nothing but this equation, okay? These equations. Now the YZZ and is by definition. This is the ZZ here, and Y. Now Y here. So this one put here, and then there is a cosine theta, and then a large Y. And then there is you need to scale this. You need a scale of this, and then you can expand. There is a term here. There's a term here. There could be a term here, and there's a cosine theta, and then sine theta can be out of integration because they are independent of a cross-sectional area. So the this one by definitions of I. Here, here, here. And similarly, we can also define the moment of inertia here. And we now use these equations and put it here. And integrations. And this one is also this term and this term and this term. And IYZ, same, we multiply of these two transformations and simpler like that. Okay. Well, I just skip the derivation in detail. So I would like to simplify, summarize these transformations and this. Okay, here is the ZZ and YY is reversed, but that's not a big deal. Well, maybe this is the equations, so we can simplify. Now, make it maybe very confusing. This is the YZ and this is small yz. Well, it doesn't matter. I will give you a very important tips like this. So there is a y and this is a y. What is the angle between the y and y? So this y and large y and small y, there is a theta. So whatever angle between two axes, I would say cosine y and small y. The first one will be the y and the small y will be a theta. I mean this will be a theta. So this is simply cosine theta. There is another one, y and y. So this is a cosine. We have a cosine scale. Now here, no matter what angle, we always have a cosine. Okay, this is the point. Cosine, whatever it is, a cosine. So here we have a y and z. y and z, y and small z. What is the angle? This is the uh, pi over 2 minus theta, because this is a theta, right? And then cosine of this, what is that? Cosine of this will be a sine theta. That's why we have a sine theta and sine theta. Now here, y and here is the y and large y and large y and large Y. What is that? Cosine theta. And there is the large Y, and uh, and there is some confusion here. So you know what I'm trying to say? Always there is a two axis, and there's a two angle and two axis makes the angle, and then cosine theta. Actually, there is another one. I'm gonna There's a misspell here. So the YZ, and actually there is another term IZY. Okay, YY, YZ, and ZY. So we apply the same principle, and this is the angle. Will be angle. No matter what angle, we always have a cosine. And same here. So this one and this one is the same. That's why we have a twice cosine and sine theta. There's a minus there. There is the principle. So we don't need to repeat. We just have a twice over here. The same rules here. Even small yy, and then large yy, large zz, and large yz, same thing. Always a cosine of y and cosine of y, and also y and z, always a cosine. We can see what is the angle. Sometimes the angle can be this one. Sometimes the angle can be this one. We know the cosine pi over 2 minus theta will be a sine theta, and cosine pi over 2 plus theta, what is that? This angle will be minus sine theta. So using this relation, we can always simplify this one. And this can be further simplified like that. The cosine theta will be 1 plus cosine 2 yes, 2 theta, 2 theta. This is the relation. So we apply here, then we can have this equation. Well, I just want to remind you that this transformation is exactly same as the stress transformation. I'd like to go back to the, oops, not this one. We spend quite a lot of time to drive these equations. Okay, these equations, and this is the exactly same. You can see that x prime and x, and x prime and x, there is a cosine, and x prime y and x prime y, and sine and sine and sine theta. X prime and x prime y, there is a cosine and sine theta, and there will be another one, sigma yx, which is the same as sigma xy. That's why we have a twice. So the point here is that you don't need to remember anything. We just, the follow these rules, uh, then you can transform uh, to physical quantity in any axis, even stress and strain or moment of inertia. Why is that so? Simply because they are second order tensor, and even though their physical meanings are quite different, but their mathematical representation or transformation will be remain the same. Okay, that's why once we have this expression, we can have a more circle to calculate the other quantities. Okay. Uh, there is a little bit of a confusion of a notation. I will summarize here again. Say this doesn't matter. Y, or Y is easy. And here you have just expand Y and the ZZ, and this is a YZ, and there will be ZY, right? So what will be the term here? And this is the always this is the Y and Z. This is summarized, okay? This is a small y and z. And remember, this is a theta. And always these two guys, okay? Two guys, there will be a cosine, say, uh, uh, well, y and y. Then, uh, okay, I will generalize the expressions. Say, uh, x x is 1 and x is 2. This is the angle of cosine, meaning that if x is 1 is a y and x is 2 is a small y, then what will be the angle here? Angle will be y and y is a cosine. I mean the theta. This will be the theta, then this will be simply cosine theta. Well, I don't need to repeat, but uh, I don't want to confuse you, but simply you have an angle cosine, okay? And this one is angle cosine, angle cosine. That's all you need to remember. This y, and there's angle cosine, always a cosine. Always a cosine, you multiply. That is the rule. That is the mathematical rules, and which can be applied to second order tensor. Moment of inertia and stress and strain are all second order tensor. Okay, that way is very easy to remember. And once you understand, well, you don't need to repeat to remember. You just use the other simple, the tools and something like that. You can say once you understand, I would say, hmm, Just 1 second, please. Speaking of AI tool, you don't have to use the ChatGPT. If you prefer, you can use the Gemini. Gemini is also a great tool. Uh, but I'm just, uh, I mean, myself are using the ChatGPT, but there won't be no difference. Okay, well, if you want, I can just use, say, okay, let's say we use a Gemini. Man, I'm sorry, I have some trouble with the keyboard today. Hmm. Uh, I hope you guys can read. Uh, say how to transform the I would say second order tensor. Okay, simply typing like that. You can try to type, but the when you guys use the AI tool or method, the most important point is the prompt. Prompt means you know what keyword, what sentence you are typing. So this is the one I just type and see what's their response. Second order tensor, how to transform the second order tensor. That's the key point. So today is very importantly we understand the meaning of uh, mm, mm. So there is a derivation procedures. While some you know the why we have a such rules is that two quantity like the here we represent, I mean this Gemini represent the t, but t can be a moment of inertia or stresses. So the actually the here is a cosine theta, sine theta, and here is a cosine theta. So you multiply, you expand them, then you will see the same results. Okay. So that's why the first term will be cosine cosine, and the sine, and then exactly like this. So the we can have these terms. Okay. You can expand that. You can simply, I mean, we will have the exactly same as here. Okay. Now, another very important issue is that the shear stress uh, in beam theory. Okay, we will have a. Okay, it's a 3:07. Let's have a 10-minute break. Okay. So let's see you. I'll say let's see you three about 20. Okay. See you. Make sure that we got this shear stress in symmetric elastic beam. What does it mean? Shear stress in symmetric. You know, the we relatively didn't pay much attention to a shear force. We did uh, emphasize enough about the all the moment, but in beam theory, we do have a not only moment but also a shear force as well. The shear force, you know, like the whole cross section carries the shear force and moment. We uh, went through what kind of stress we have, such as moment. What does it mean? In terms of a stress is a linearly varying stress. This will effectively cause the moment at the cross section. So whenever we say the moment means that we have a stress distribution like that. Okay. So material failure will be determined by the maximum stress or compression or tension. That is the main point of a design of a beam theory. Now, how about the shear stress? I mean, shear force. This is a moment, but as you can see that beam theory, when you go through, you know, the derivation, you would come up with this moment, shear force. See, everywhere the shear force like that. So shear force, what kind of stress is related to a shear force? Uh, the that's the one we like to study. You know, this shear force. Every cross section would carry the shear force in addition to a bending. See here, we already have a shear force, and everywhere shear force in addition to a moment. Okay, and then again, the moment is related to a linearly varying stress, but how about the shear stress? That's the topic we like to cover. Okay, so cross sections, we have a shear force V and the bending moment of moment, and this guy, the moment, okay, the stress wise always like this. Okay, this is a sigma x, and this causes the moment. Now, the shear force V, okay, shear force V, what kind of a stress would be equivalent to, this is equivalent to a moment. What kind of a distribution would cause this shear force? Well, that's the point we like to discuss. Uh, So, for sure, the shear force will be caused by sort of a shear stress, like a distributions. Okay, that is for sure. But how distribute? What kind of this? Sometimes we call shear tau, or we can call it. Uh, See, this one is a Z, and this is the Y. Then will be a Y and Z. Z plane, Y direction. That's why we can call sigma YZ. Or in short, we can call it tau. So tau stress. What kind of distribution is that? Uh, uniform like this, or uh, can be what kind of distribution. That's what we like to do. As a result, for sure, this will be a sort of a tau. The A will be a V, but we don't know in detail how this distribute. That's what we like to do. Okay, okay. So again,
교수님 죄송한데 화면이 안 보입니다.
공유가 안 됐어요? 뭐요?
그런 것 같습니다.
아, 이게 미안해. 이게 줌이 좀 이게 보존압이 되면서 내가 여기서 화면을 이게 옛날엔 표시가 잘 됐는데 지금 됐어요?
네, 됐습니다.
네, 오케이. 네, 지금 화면을 세 개를 동시에 쓰고 있어가지고 이게 어떨 때 나타나고 오케이. 자, 요 다시 한번 얘기를 할게요. 레코딩은 되고 있죠? 음, 오케이. 알려줘서 고마워요. 자, 빔에서 크로스 섹션에 V하고 모멘트가 항상 존재를 합니다. 그리고 모멘트는 지금 이렇게 응력이 이렇게 선형으로 바뀌는 걸 우리가 배웠어요. 근데 포인트는 이 시어 포스 이 시어 포스 V가 이렇게 단면에 이렇게 평행해서 가해지는데 이게 결국 이 시어 스트레스가 분포해서 이제 존재를 하게 되는데 이 시어 포스가 어떻게 분포하느냐가 지금 핵심입니다. Again, the main point is the shear stress on the surface. Uh, there will be a shear stress. And what kind of shear stress will cause the V? And in other words, V. What kind of a shear stress will this V shear force will cause? That's what we like to study. To do so, we have a little back to the equilibrium. Say we have a very long beam arbitrarily, and there will be some x here, and there is some dx here. So, say we have a distributed load. This is the generic definition of a beam. Now we paying attention to this small, the dx here. So dx on the left-hand side, where the x, we can simply say the v and then a moment. And the positive side, this is a x plus a dx. So we can have a sort of a moment, and the m. The reason we don't have a dv is that we could have it, but we just say neglect uh, the shear force in these regions, then we would not have the moment. You know, the dv dx the plus q equals zero. This was the vertical equilibrium, dv minus q dx. So not only just mathematical, but also physically, we need to understand this. It's not that difficult. see dV, increment of shear force on the right-hand side will be equivalent to the Q, which is applied over the dx. If this is a zero, then no dV. So to make the simplify, we have a neglect Q. So such as let's say we have a clamped beam like this, and then we have a V here. I mean, say this is a concentrate. I would say this is a V0. This is exactly the same case as the eVTOL. You know, the eVTOL, we have a motor vertical, and this will be the main body, and this is a very typical case. Now here, we don't have any, the Q here, right? But any cross section, there will be sort of a shear force. So the you may wonder, oh, how come there is a no distribution and how come there is a shear force? Well, the shear force increment may disappear. We may not have an increment, but we could have some constant V. So constant V here, positive side. And then a negative side is a minus, an increment. Okay, so this is the kind of a starting point, how we calculate the V. Uh, Now, from equilibrium, we do know that moment dm and this m would cause uh, the stress sigma x like that. We do know that this is the equilibrium between the moment and sigma x. So we do know this one, and then we know this sigma. So left hand side and right hand side, there is some little bit of a difference in this distribution. Okay. Now here on the right hand side, x plus dx, we have a increment of a moment. And as you can see, it's not quite clear. We have a more tensile stress than this one. Okay, this is the case. This is the case, and we need to know that this moment equilibrium wise, this is the moment, and this is the moment plus d moment, and this dm disappear. This dm is the moment like this will be caused by the shear force, this v and this v. See, this v and this v will make the this rotation, and this dm so VDX, VDX will be same as the DM. That's the moment equilibrium. That's just a remind. And as we reviewed the last class, we have a two equilibrium, and this is a moment equilibrium. Again, I just like to emphasize that moment here would cause this much stress, and a moment here is this much stress. Now we have a little bit of an increment. We have a little larger, I would say, larger stress here on the right hand side, on the larger than the left hand side. Okay. Now, what will happen here? If Okay, I will just draw here. We have a little bit like this, and we have a like that. Now we take a look at only this part. Okay, only this part. That is this guy. So on the right hand side and the left hand side, we have this one is the resultant. Pay attention to this only this small piece. The one thing very important we need to understand is the either small or large, every part needs to be in equilibrium. In equilibrium. meaning that this part also, this guy has to be in equilibrium. Okay, in equilibrium. So this force will be larger than this. Why? Well, again, this sigma x equal y moment plus dm, right? This is the dm, and here is a smaller than this moment y. So we do have a little bit of a difference between these axial stresses. So if we have only this and that, there's no x equilibrium. X directional equilibrium is not x equilibrium. 오케이. 중요하기 때문에 다시 한번 얘기할게. 이 크로스 섹션에서 요 위에 부분 어떤 포지션, 뭐 이게 Y라고 이런 긴 빔 중에서 요 부분만을 이 긴 빔 중에서 일부분을 뗐고 그 중에서 또 we have a little part upper를 했을 때 오른쪽에 엑시얼 스트레스와 왼쪽에 엑시얼 스트레스가 달라요. 왜? 모멘트가 다르기 때문에. 모멘트가 다르다는 얘기는 시그마 X가 다르다는 얘기예요. 그러니까 이놈이 어떻게 되겠어요? X 방향으로. 예? X 방향 평형이 안 이루어지죠. X 방향 힘의 평형이 안 이루어진다. 그게 지금 핵심이에요. 그럼 X 방향의 평형이 이루어지려면 뭐가 있어야 돼요? 어딘가에 X 방향 힘이 있어야 된다. So to make this one in equilibrium, we have to have an additional X directional force. Then where does this additional X directional force can come from? From the bottom surface. This is the bottom surface. This will be the X directional stress. We don't know the amplitude and magnitude, but we do know we need to have this one to make this one and this one and this one all now can be equilibrium. So that's the whole point. Whole point. So we like to know, we can now see how much the force we can have it, and then we always know that the stress, you know, on two vertical surface, we always have a sigma xy equals sigma yx. Why? Because it's a locally moment equilibrium. So we do know this. So we are studying of this bottom, and bottom has to be from the equilibrium in x direction, and then this will be same as the here, okay, here locally, here. So that's the one, the logical procedures. So on the right hand side, again, this one, right hand side, we have this much stress. On the left hand side, so we have this much stress. And then bottom, we don't know the shear stress, but the shear stress times the dx times this is the say this is will be a B, the width of a beam. So we multiply the B. Okay, so every three terms, summation of three terms will be a zero for this beam to be in equilibrium. Okay, so here, the pay attention is a tau here. Okay. So as you can imagine that, okay, this moment and moment disappear, that this moment increment will be the same as this one. That has to be equation-wise. So the next one is like this. Here, one other point here is the dm. Okay, dm. Well, we know that dm is what? V dx. Increment, this is the one thing we know from the equilibrium. Okay, from this one, we know the equilibrium here. So dm can be replaced with a v here. That's here, and then this be can go into the formula. Now to everything simplify, this is a b. This is the force, and this is the from the moment, and the moment is here. So and the v can be out of integration, and I can be out of integration. Only thing is that yda, our let's use the q to represent this one as a so vq. This is a tau, and vq vq I v. Okay, I know it's a little bit complicated. So v q and I v. So v is a constant, I is a constant, v is a constant. Only variation is the q. Okay, remind that what is a q? Q is that integration of a yda. Yda. So yda, the integration means that over here. So here, only this part, we will have I will draw like this. And this is the Q equal y dA. So y is here, and then x is here, and this is the y. So y dA integration, only this part will be the Q. Okay, so this tau is a function of y, and Q is the function of y. Now, so this is the equations result. Well, this is the mathematical equations, but more importantly, let us understand the physically. So this is the shear stress we have, and this is the axial forces, and this is the axial forces. Again, this axial force is greater than this guy because we have a dm. It's now not in equilibrium. So to make the equilibrium, we need to have this shear force. So this is axial forces, axial forces, axial force. So from that, tau can be calculated. Now this tau is always the same as here. Okay, same as here and same as here. And then if we consider more area, same thing. We have a more area and more area. So this difference between this guy and that guy, we have a shear force, and that is calculated numerically from this equation, and that is the stress, shear stress at this point, and so on and so on. So if this is a neutral axis, this is a whole stress, and this is the on the right-hand side, the left-hand side, there is a difference, and that's the amount of stress, shear stress will be caused to make the equilibrium, and this stress will be the same as this one. So that is the how we got this detailed shear stress from caused by the V. Okay, to make the long story short, the maximum shear stress, what's the maximum difference between this force X and on the right-hand side and left-hand side? Well, at the bottom here, this will be the maximum, and then gradually decrease. So shear stress-wise, always like this. At the middle is the maximum, and gradually decrease top and bottom. Okay, which is quite different from sigma x. Sigma x is much larger than top and bottom, and then a zero here. But is a quite different shear force as a maximum at the shear and zero at the approaching to zero at the top and bottom. Okay, uh, mathematically you can drive this one. So let's drive that one. And then y and integration and y is dy, I mean y square and integration from y1 to top. And then you got equation. You can see that this is exactly parabolic equations. So if y1 equal h over 2, this will be a 0. But if y1 equal 0, this one will be the maximum. Okay, so that's why we have a maximum like this here, maximum. Okay, uh, well, you guys don't need to remember any equation, but do remember, do understand the physical meaning, why maximum at the center and how this shear stress is distributed. We can calculate from this equilibrium. Okay, here. So at the maximum, we have this, where y equals 0, neutral axis. And then plus or minus top and bottom, we have a 0. This is the, you need to remember, this is a parabolic. Okay, well, let's try to compare the stress-wise. See how much stress, let's say, for example, we have a P here, we have a moment here. The moment, the maximum moment, I mean, variation will be like this, right? 0 at the top, and the maximum here is simply because the moment here is a PL. Now, V is the any cross section. You have a shear force of V equal P. That's why we have a uniform. Now, the point is that the tau shear stress will be like that. From previous, like to emphasize that here is the 3 over 2. This is a 1.5 times V over BH. What is a V over BH? BH is the cross-section area, and V is the shear force. Simply force divided by A, cross-section, and 1.5 times. So 1.5 times bigger than average. This is, you can say average, right? V divided by, the BH. This is the cross section. So maximum is always 1.5 times bigger than average. So that is the maximum. Now, how about the maximum stress? Well, stress, it can be a moment, I, and so on. Moment is what? Maximum will be a PL here. And then Y is H over 2, and I is the pH square, pH 3 third power, and then 12, and we got this one. So what we like to do is to compare this guy and this guy. So we divide by this and this, and then we can simplify something here, and then P, and then we got this. Okay, I mean some constant there. This gives us a very insightful meaning that sigma x can be very larger than tau stress. As you can see, L over H. What does it mean? L is the beam length. H is always a small h compared to L. So shear stress, even though it's a maximum at the center here, okay, center here, but the maximum shear stress will be much smaller than this, bending stress. This maximum is always order of L over H. So that's the reason we often neglect the tau stress, but when we consider equilibrium is very important. Again, the shear stress is a zero at the top and bottom, maximum at the center, and this maximum is still very small compared to a maximum, the tensile stress. So that's the message we like to understand. Okay. So again, the compared to this sigma x, tau is very small. We don't consider much when we consider the equilibrium and etc. So back to the 3+1 flow chart, we always need to, here, the equilibrium and the stress has to be less than strength. We do know the strength of the material, and the stress has to be less than this. Okay, that's the one I like to separately emphasize in the beam theory. Okay. And there are another other bending of unsymmetry and shear center, but we're not gonna cover that part. Only this uh, say these two. Oops. This is the one we like to emphasize. And the singularity function is the mathematically useful when we solve them using the force of the differential equations in beam theory. Okay. Uh, let's see. Just 1 second. Okay. Well, as before uh, we have several subjects in ChatGPT, and also again, you guys can still work on the Gemini or other tools. And here we can define the say moment inertia or transformation of, I would say, uh, well, just say uh, sometimes we can call them bending moment of inertia. Okay. Sometimes we often call them moment of inertia or second order of moment of inertia. And let's see what they say. The bending moment of inertia, often just called the moment of inertia or second moment of inertia. Definition for a area A with a neutral axis. Okay, this is a neutral axis, so we can have a y scale dA. Well, sometimes it doesn't need to be a neutral axis, but this is the moment of inertia. And if this is a rectangular, we will have a BH3 and 12. This is the equation you guys need to remember. And then a rectangular, and then about the base with respect to bottom surface. This is a neutral axis. This is the bottom surface, and this is a circle, a pi over force. See, BH3 means that dimension you have a four times, right? Four times. That's the one you remember. Four R4, and then if this is a circular, I mean the tube type, then you have a minus, and then scale. Well, scale is easy here. B and H, if they are same as the B, this is the one, and things and that. Y in matters in beam bending. This is the EI Y double curvature, and then you can say how to transform the moment of inertia. Uh, we have a transform, meaning the rotation, and translations. Uh, this is just the coordinate transformation trend. See, this is the equations. Okay, this is the equations, and the exactly same observation in the stress. The maximum shear stress, maximum, and the principal, exactly same thing can appear here. And translation, parallel axis theorem, and this is the one we just covered that. Uh, my point is that you guys don't need to fully remember any equation, but conceptually, this is the topic we are touching, we are going through in the beam theory, and then so uh, why those the I would say moment of inertia. You guys can keep asking and communicate with this AI. See, I can deliver the courses and knowledge as much as I learn, but the ChatGPT can cover uh, more than I can. So it is worthwhile to go through. And then why this moment of inertia and things like that is so important. So it can give you some meaning. Say, well, they suddenly changed to Korean, but parallel axis theorem, and meaning that once we have a moment of inertia with respect to one coordinate system, we can have the other one easily. So as you can see, practical engineering case, beam design and aerospace and automobile and composite everywhere. This is the one uh, we need to understand this. Okay, so uh, now the another one I like to say is that how to calculate the shear stresses in a beam, say subject to the shear force. Uh, okay, how to calculate the shear stresses in a beam subject to a shear force. That's the topic we just covered. That. Let's see what it says. Uh, well, how to calculate the transverse shear stress tau in a beam is the Q, we define the Q, same as area above uh, cut. Cut means that, we also consider the cutting area, so Y prime dA. So shear force is a VQIT, a little different definitions, but this is also important. And then, and so one thing the Q, I mean, the tau maximum is that, the, okay, not the inward, the, okay, this is the one. V over A, solid rectangular, V over A is the average. We have a 1.5 times bigger than, the averages. This is a tau maximum. Uh, so the shear force uh, will be will distribute to here. Now let us ask why the shear stress can be important uh, even with a very small magnitude compare with maximum bending stresses. See, this is important to understand. The bending stress, sigma x is very large, but the shear stress is small. But Y shear stress can be important even with a small magnitude compared with maximum bending stress. Let's see what it says. It would say something like the Van Mises, well, this is a failure criterion, and the Tresca Van Mises, because in the middle of somewhere there can be some multiple stresses, not just the compression, but also shear stress. That's why it says that we may need to consider uh, tensile stress and shear stress together. Okay, that's the one point. Uh, and the well, not much the main point, but you guys need to understand in your own way. Tau, in short, tau seems small. It redistribute the energy and affect the failure and couples layers and in real things. Okay, so um, that's the topic we can covers today. So we have a certain point. Now, the that's the kind of overview of the our class in this beam theory and special issue. Next one is the buckling. But less rather than before we go to buckling, we like to cover more about the uh, practical applications. Say uh, okay, beam theory in eVTOL design. This is the one topic we went through. Uh, how to use a beam theory in the design of a eVTOL, and we cover this where beam theory fits in the eVTOL. Uh, okay, just want to share this one. I recently shared this news with you through a Kato, and the China air tax eventually just they started. This is not a just plan. Is released a few days ago, only 3 days ago. They announced that in China, this is the Yihang, we consider in class, uh, from Guangzhou to Hefei. Guangzhou to Hefei is that, say, let's see, Guangzhou is here. Actually close to Hong Kong. Okay, this is Guangzhou is the a lot of advanced technology cities and the IT and a lot of companies here. And the other one is the Hefei. Hefei is here. Hefei is also another city. A lot of the new technology, Hefei. So from Hefei, Guangzhou to Hefei, there will be a certain the airplane, the taxi. So the they are trying to China. They are trying to cover from here to there by the Airbus. I mean the eVTOL, flying car. So this is the very wonderful news. And the I will say, what is the distance between say Hefei to the Guangzhou, space what J or G, G, G or okay. Well, the reason we like to see the distance between the Hefei to Guangzhou is that approximate distance from between the Hefei to Guangzhou is it's a 1,000 kilometer. Okay, 1,000 kilometer. So the 1,000 kilometers is not a short distance. It's almost the twice larger, longer than between the Seoul and Busan. So when we design the eVTOL, we have to make sure we cover this much length, 1,000 meter. And by car would take the 12 hours. Would take a 12 hours. say how long will it take? Uh, say if we talk. Let's see what it says. So the eVTOL, this is not the just a plan. It's a big movement globally, and the so it's order of 3 hours and things like that. Well, not so much meaningful, uh, but importantly, the everywhere, every country like to launch this new project, and the even Hyundai, uh, Hyundai Automotive, they are called Advanced Air Mobility. Advanced Air Mobility, 미래 항공 mobility. It's a little different names, but there's a huge plan. The, so the mobility wise is similar to a regular vehicle, but AAM, Advanced Air Mobility, is the for future air mobility. So the uh, So we often need to understand what it means, eVTOL, vertical takeoff, uh, and there are lots of activities, and recently there is some. I remember we saw some. Okay. See, Sosan, yes. Hyundai Mobility Group announced that they launch AAM Center in Seosan. Uh, okay, here. Oh, this is just 1 day ago. This is November 7th. This is 1 day ago. The topic we are going through is not the plan or not the all a long time ago. This is a current activity in China, in Korea, and also United States. So the AAM cluster, huge cluster in the our Chungcheongnam-do, Seosan, and they have a big center. So that's why I like to often remind you of what you can do as a mechanical engineer, what you can do as I mean, while you are learning about this solid mechanics. So location-wise, here is the out. No, I think the somewhere here, Seosan, and then is a little bit closer to Hyundai. automotive. I don't mean to just emphasize Hyundai, okay? This a big company, but uh, you guys also pay attention to a small uh, startup company, or sometimes you can create your own company with your idea and knowledge and your visions, and also well, I just wanna emphasize the current trend. Okay. Well, how to use the AI to better learn the subject of solid mechanics? That's the one I like to emphasize. In addition to the conventional, the course. Uh, Again, I feel very urgent that you guys make a full use of this AI approach and tools as a mechanical engineer. Otherwise, you will be. I don't want you guys behind of a trend. AI is the one you have to push yourself to get in harmony with the trend. Okay, so as I design, you just enter like question yourself. Okay, question yourself, and then learn what they are saying. Tutorial is will be AI will be a great tool for the tutorials, even much better than my tutorial. And then problem solver, you can generate the solve and then check. But to solve the problem using the ChatGPT or any AI, you need to know the theory, and then you need to know the subject. If you don't know about the beam, the stresses and things, you cannot communicate with the AI. So you should know that, and then you AI can be a great problem solver. And also design wise, a design assistant. You guys remember uh, we simply use the nothing but the AI to get this kind of distributions. Not only we are learning new things, but it saves us a lot. We learn a lot very quickly. I don't mean to just rely on the ChatGPT, but to get the real design problem, uh, we solved a lot of the uh, problems so that we can move faster. The speed is the power of the competitions. So thanks to AI approach, we can move very quickly. And the computational framework builder, that's the one. Learn how to think like the mechanician. See, with this AI tool always with you, this can be used as one of a part of yourself as a designer, and so many things. Then we had this one, this we can define the project, and then we can have a sub project like this, so that we can always go back. to each subject. Now, this tool can be used. Well, you can use many other tools like the Excel or Python and any other computational and also CAE tools. But this it can be as one of the tools. Uh, Say, what if the distribution load? Uh, what if the distribution load? Uh, I would say linearly varying rather than a constant. Well, I would say uniform. See, last time we consider the uniform load, and then we got the maximum. We found the optimal distance. This is optimal distance to support. We can get the minimize. We can minimize the moment. Uh, but what if the distribution load will be linearly varying? So instead of this, we can have a linearly varying. I will clarify from 0 to the maximum at the end. So my point is that this conversation and this tool can be used as a not just to get a insight, also get you can get uh, a heavy calculation part, and by communication you can discuss with one of the world best, and then you can learn. So you guys need to communicate with your, I mean, considering your basis and your experience. Well, I just made up this story, but this is one thing you can do that. You can use it as a one tools. Same for ChatGPT. Well, I hope that you guys we can move to next level of ChatGPT, like the establishing the tools, but uh, would take a little more time. See, it takes a little more time. Sometimes uh, the calculation itself takes time, but also sometimes the prompt is unclear. Then it takes some longer than clear prompt. So when you before you type, you need to clarify the question you have. Otherwise, uh, this ChatGPT consider all the possible cases and then trying to get the best. Uh, they're trying to estimate the best solution and estimate the best question. So the triangular load from 0 to W0, I mean, is here like that, and it says the maximum moment and so on and so on. I don't mean to get the real meaning, but the maximum stress. See here, the maximum at the top center here And here is a optimal. You can have this magnitude, and that magnitude will be the same. So, well, I don't mean to emphasize the exact value, but my point is that how we can do with this tool, and we can use that as a design tools with your own problem statement. Okay. Uh, okay. I just want to show you that the shear stress calculations at this subject. Uh, please plot the shear stress, I would say, distribution over the section. Well, let's see. Plot what we like to see that shear stress is a parabolic at the maximum at the middle, and then top and bottom is a zero. That's what we like to see. I forgot to mention the rectangular, but let's see. Plot the shear stress distribution over the section, rectangular section. I forgot to mention that, but I hope that they get give us the sort of the parabolic and with a maximum at the center. Okay, this is the one. You see, this is the at the middle we get the maximum, and then top and bottom is the zero. And then the value we get is the previously we have a certain magnitude and etc. That's why we get some value. But the point is that we have a maximum here, 3 megapascal. Value is not so important. Point is that the parabolic profile, parabolic equations, second order. That is also important. So okay, V is a total the 20 kilonewton, and divide by the cross section will be the average, and average will be something like this. Okay, and then this is the uh, 1.5 times of average. That's the point I like to emphasize. Um, you can simply say the what is the average shear stress. I'm sure you will say the average will be I would say 2 megapascal because it is a 3. So 1.3 times means that the 2 megapascal. See here, this is exactly what we learned. Average is a V over A, that's the average, and then a parabolic, and then it's a 1.5, and then maximum is a 3, and then average will be 2 megapascal, and so on. Okay, so this is the topic I like to cover today. I just touched the extra issues relate to a beam theory, and most importantly, the applications. Rather than just staying in the lecture note, you guys need to move to a real application. How to use that? uh, rather than just the remember, or rather than just the stick to just a theory, but now with your own imaginations, and then approach, you should be able to design real structures. One typical one is the eVTOL. So please try to get more used to eVTOL and so on. Okay, okay. That's the all the subject I like to cover today. Okay. Uh, Thank you so much for attending the class on Saturday. Uh, and then I will share the YouTube class as well. Okay. Bye.